Hello and welcome to another Piper Pod. Today I'd like to start what I hope to be a 4-part series of cardiac lessons. The reason we've chosen cardiac lessons is obviously it's a hot topic, something people have a lot of trouble understanding. So part 1 of this particular lesson is going to be on the conduction. Okay, so we're going to be focusing on the factors that influence the way the heart conducts and the way neurons interact, and essentially the starting point of everything else to come. Okay, so without a good understanding of this, I believe it's quite difficult to get your head around certain drugs, electrophysiology, and even arrhythmias. Looking at the myocardial sites themselves, we all know that they're quite unique in the way that they react. So there's 4 main characteristics that are found in myocardial sites that's not found in any other muscle cells. Okay, even the neuron clusters are quite unique around the heart. Okay, so the first of those characteristics is that it has something known as automaticity. Now when we look more into arrhythmias, we'll look further into this automaticity and we'll look at the rates of each particular area of the heart. But in a nutshell, essentially, without giving too much away, the heart has the ability to beat itself. Okay, so in the absence of any external stimulus, the heart will be able to generate an action potential. Now, when we start looking at ion movements and the factors, you will learn why that is. Okay, but we just need to keep in mind that automaticity is a thing of myocardial sites. They can beat without any external stimulus. The second is they're excitable. They have excitability. So they have something known as an action potentials. Okay? They're able to be stimulated by external or internal stimulus, and it's that excitability that allows the heart to generate its contraction. One that complements excitability is its conductivity. So once a single myocardial site is excited, it has the ability to transfer that excitability onto the next. So it works a little bit different to the sliding filament theory of muscle contraction. Okay, it works as a ripple effect of contraction. So once it gets excited, it actually works as a conduction down pathways ideally that allow the rest of the heart to contract around it. And with that conductility, obviously, it comes with the functionality of contractility. Okay, so when we talk about depolarization and repolarization, it's really easy to forget, especially if you study neurons. And depolarization in neurons literally looks at the ability to pass that electrical signal along an axon. It doesn't actually correlate to functionality, but in the heart, the depolarization, because of the other characteristics of excitability and conductiveness and contractility, it actually relates to when the heart depolarizes, the heart also contracts at the same time. Okay, very useful function, obviously. Okay, so they're the 4 characteristics of a myocardial site. Okay, what makes them unique in the body and allows them to function. What we'll move on with now is we'll spend a little bit of time looking at those ion movements. We've touched on ions in the past when we talked about fluid physiology. Now we're going to talk about the other factors that affect ion movements, especially focusing on the neuron. And remember, as I mentioned before, that when we talk about neurons associated with the heart, that neuron activity is also correlated to contractility. So I'll try to go as slow as possible with ion movement, and we'll talk about a few things that need to be understood before we look at the cardiac contractility. It gives you a better understanding. So to start us off, nice and easy, the first law or factor that affects ion movements is diffusion. Now we've looked at diffusion in the past, and associated with fluid. Okay, it's obviously the diffusion that increases the osmotic pressure that draws that fluid that we talked about before. Diffusion, just as a means of recapping, is in relation to ions moving from an area of high concentration to a low concentration. Okay, so when we look at things like depolarization, repolarization, resting action potential, we always talk about inside of the cell in relation to outside of the cell. I don't think anybody's confused by diffusion. You have a large concentration somewhere, and essentially that's going to move into an equal concentration on the other side. Okay, so it has that moving power from a high to a low concentration. What we need to take into account is that's not the only thing that plays a part in contraction and ion. I know when we probably learnt this in action potential in high school or in early medical training before really looking into it, it was essentially just said, oh yep, the sodium, the potassium, they swap because of diffusion. Because there's lots of sodium on the outside, lots of potassium on the inside. So it's that natural movement that occurs. Now, the guts of it is true, but as you could imagine, the complexity is not quite that simple, because if it was, essentially the heart or any neuron wouldn't function. Okay, so we need other laws that need to complement this basis of diffusion. The second law in ion movement is the Ohm's law of drift. Now obviously Ohm's laws and Ohm's theories and Ohm's is always looking at current and conduction. So it's no stretch to understand that the Ohm's law of drift, when dealing with neurons, is referring to that ionization, okay, that actual particle charge and how it affects movements. So just taking it back a step, we need to remember that ions are broken up into cations and anions. Okay, cations have a positive charge and anions have a negative charge. Okay, but within cations, they have a greater ionization potential. Okay, so not every cation has the same charge. It's not just that plus equaling one charge or one figure. Okay, they have a different amount of charge associated with each particular ion. So when we look at Ohm's law of drift, what that states is that ions will be drawn to areas of their opposing charge. So what that means is if inside the cell you have a whole bunch of cations, and therefore outside of the cell is relatively negatively charged, then Ohm's law of drift is going to pull those positive ions to that area. Ohm's law of drift is a pull, if you will, to an opposite charge. So a positive will want to go to a negative environment. A negative will want to go to a positive environment. And as we'll learn, a relative negative cation will want to go to a positive environment. So when we look at each one of these rules, these two rules is what's going to play the biggest role in ion movement and really understanding how neurons work. Okay, when we start looking at ion channels and things like that, you'll learn that these two really work hand in hand together. But you need to understand that they're not the same. Okay, they are not the same. They are what's known as additive rules. Okay, what that means is if we take a well-known concept, let's just say we have potassium, high amounts of potassium inside the cell. Now diffusion will state that those potassium will want to move out of the cell because of the concentration gradient. The Ohm's law of drift states that those potassium ions will want to move as a result of its relatively negative environment inside the cell to wanting to move to the relatively positive environment outside of the cell. They are two factors that will draw on ion movements individually. Now they can be additive in the case that we just spoke about. Okay, potassium has both a diffusion and a drift need. It can also be exclusive. It means that if you have a gradient pull one way and a conductive pull the other way, then they'll actually cancel each other out. Okay, and that's what's known as equilibrium potential. Because what some of you may be thinking now, with these two laws acting together, you pull a relatively negative out, it's going to want to drift back in and then diffuse out and then drift back in and diffuse out, so on and so forth for a long period of time. Now, this happens, but it doesn't happen indefinitely. Every single ion has its own equilibrium potential. Now, what that means, its equilibrium potential essentially means that its gradient pull is equal and opposite to its conductive pull. Now, for those that love physics, okay, you can look up something known as the Nernst equation that will tell you, and you'll be able to figure out each particular ion to find out what its millivolt charge is or amp charge is that relates to the equilibrium potential. But for the purposes of this, potassium will keep moving in and out of the cell until it reaches an equilibrium potential of around negative 75 milliamps. Okay, sodium will keep wanting to move in and out of the cell until it reaches positive 50. Every ion has an equilibrium potential, meaning that once it gets to that equilibrium potential, it's essentially going to stop moving. But when that changes, then the factors are going to come back. Okay, so when the milliamps on the inside of the cell changes, moves up, gets less negative, then potassium's going to want to leave and sodium's going to want to come in to equal that potential. As you can see, they are additive to one another. Now, to put things into a body sense and a practical sense, okay, because so far we've just looked at diffusion and drift, so everyone's mind's probably just thinking that ions can move in and out willy-nilly, not much restrictions, they move the same speed, okay, and they just wait till they balance and then they're done. Okay, when you think about all the different ions in the body, you will come to the conclusion that equilibrium potential for every ion is not going to be able to be achieved, because every ion has a different equilibrium potential. Okay, so that's when this third law comes in, okay, and that's the Einstein's relation between diffusion and mobility. Okay, now this particular law gives it its practical application, because what it essentially means is a ion that is able to diffuse easily will be able to do so quickly. Okay, and ions that can't diffuse easily will be restricted within their movement. Okay, now the things that play the biggest role in applying this rule, if you will, is the different sites of ion channels that are found throughout the cell. Whenever things need to come into a cell, they need to do so via channels. Now, the problem with a lot of textbooks and a lot of automation is they can't really capture what these ion channels are. Okay, so the ion channels are not just holes in the cell that fit perfectly those ions. They are ever moving, ever fluctuating channels made of their own elements and our own cellular structure, okay? Phospholipid layer built in with essentially proteins in some ways, but every single channel has its different composition, and those compositions essentially mean that certain ions can move out of it and into it, and it makes them very selective. Now, even within its own ion channels, okay, let's look at sodium ions. Okay, there's different types of sodium ion channels within a cell. Okay, there's those that are essentially open, so they just have that permeability in place. There's some that are only open during rest. Okay, so as the actual cell membrane is in its resting phase. Okay, and then during another phase, like depolarized or repolarized phase, those channels will close because they're always in flux. There's other channels that are only opened at certain volts. Okay, so certain current will actually open certain channels. Okay, we'll explore more about that when we look into the actual conductivity. The point is, yes, diffusion and drift exist, but if we left that just to occur willy-nilly, then our bodies wouldn't function. We'd have non-stop movement of ions back and forth, so we'll never get that action potential. We'll never get that contraction that causes functionality if it wasn't for this third rule.
The final rule is a physics rule.
We have to change it a little bit when dealing solely with the body, okay, but it does play a pretty big role. We won't really be referring to it much in this particular lesson, but when we start talking about acid-base balances and stuff like that within the body, then the fourth rule of space charge neutrality plays a much bigger role. Okay. Now, the general rule, if you were to search space charge neutrality, it essentially states that a solution in any compartment will aim to have the same amount of cations and anions within those compartments. Okay, so what that means is if a positive ion moves into an area, that solution will want to have a negative ion to counteract it. Okay, so you want to have that neutrality, you want to have that equilibrium within the body. Now, in the body, it's approximately the same. Okay, anyone that knows anything about human tests, anion gaps, things like that, know that you're never going to get a perfect equilibrium within the body, and realistically, the body needs a slight difference within it in order to generate a lot of these metabolic functions that we need. So we'll leave space charge neutrality for now. We'll venture it more if I ever do an acid base. I had to put it in because it is a factor that affects ion movements within the body. Alright, hopefully you guys followed most of that. For those that are a bit lost, then hopefully these pictures will help illustrate what we were talking about with ion movements, okay? Because I'm the type of person that is never just happy looking at the pictures and going, oh, okay, sodium, potassium moving, that just happens. We need to understand why that happens, because understanding why that happens helps us have a better understanding for when things go wrong, or when people are on certain medications, or when you're looking at an ECG. It helps to give you that deeper understanding of what you're looking at. So the picture in front of you now is that of the depolarization repolarisation cycle. And this is what happens when the cell reaches what's known as an action potential. Wonderful thing about an action potential is it's all or nothing theory. So what that means is, let's say that you needed to reach negative 65 volts, okay, in order to initiate a charge throughout the body. If the cell never gets to that particular voltage, then nothing is going to happen. Okay, so what that means is if inside the cell changes a little bit, okay, so you get a small change inside the cell, ions move, the cell at rest goes from that nice negative 85 and it goes to negative 70. Then essentially the cell's just going to, move on. It will dissipate across the actual axon or the neuron, and there'll be no reaction. Okay? So if a stimulus is too weak at one end, it doesn't meet that threshold, then it's just going to dissipate across the neuron, and it's not going to have that pass-on effect. And in the heart, it is certainly not going to have that conductive or contractive effect that we want. But if that impulse goes over that threshold, then you are going to get an effect. And from that effect, the entire heart will contract as a result of that one threshold being hit. And the really cool thing is if you give it a positive 30 stimulus, you are still going to get the exact same result. So just because you hit it with a positive 30 doesn't mean that the picture in front of you is going to shoot up to positive 90, positive 120. Okay, it's not going to happen. And it's not going to happen because of those relationships that we looked at before. And I'll explain further as we move along the different phases. Okay, so it really is an all or nothing. If you don't reach it, you get nothing. If you do reach it, that or above, it doesn't matter how much you hit it with, you are going to get the same outcome. Okay, which when dealing with the heart, that's very, very useful, because you could already have the heart halfway through its automaticity of leaking in ions, getting close to that negative 65, and then it gets hit with an impulse. It's obviously going to push it closer to the negative 20s, but the result's going to be the same as if the impulse didn't come in. Okay, so very, very handy. Otherwise, our heart would be doing all sorts of crazy things. So looking at this particular cycle, we break it up into phases, okay, and those phases equate to different ionized movements. So starting at phase 4, it can best be described as the membrane at rest, or the neuron at rest. Okay, now remember that when I'm talking about the heart, the neuron relates to cardiac contractions as well. Okay, so you're both learning neuron movements, okay, and heart movements at the same time. Okay, so during phase 4, the heart is at rest. Everything generates itself. It says that once it reaches that negative 90 millivolts, then it's going to be ready to respond. Now, the mass is a little bit different across the board, but if you work with these general numbers, you'll be fine. So the actual neurobiological number is negative 85, and the reason it sits at that is because the potassium inside the cell has a equilibrium potential of negative 75. Potassium's not the only one in there. There's a whole bunch of negative aspects within the actual cell, which gives us that negative 85. When it's at rest, okay, you can say negative 90, you can say negative 85, it doesn't really matter. The point is it's negative, and at rest, the membrane is permeable to sodium and potassium. Okay, now when we're dealing around the clusters of the heart, okay, it is mostly permeable to sodium, and that's where that automaticity comes from. Okay, so we'll revisit that later on. Okay, so that all we need to take from phase 4 is this is the resting stage. This is when the membrane itself is in its negative optimal level, okay, ready to respond. Okay, it's not going to get any further than that. It's not going to keep going. It's going to sit along that equilibrium level and just wait for stimulus. And that stimulus is obviously hopefully going to result in the action potential later on. Okay, so just remember at this stage, permeable to sodium and potassium, and it's because of the leakiness of these two ions within the SA and the AV node that will give us the ability to get to that threshold that will start that action potential. So as sodium moves into the cell, sodium being slightly more positive than potassium, obviously the millivolts are going to decrease, being negative. So as sodium moves in, and a little bit of potassium moves out, mostly because of sodium moving in, the millivolts is going to decrease, get closer to that threshold. Okay, now when the impulse reaches that threshold, then something pretty cool is going to happen. And it needs to happen in order for this rapid depolarization to occur. So if we work on the resting membrane, bringing it back to rule 3 of diffusion and mobility, at rest, only certain sodium channels are open. Okay, and they are those general permeable sodium channels, meaning small amounts of sodiums are leaking in. Okay, so there's not many channel open, basically, is the best way to look at it. Okay, so only some of the gates are open. Once it reaches that threshold, voltage gate sodium channels open up. Okay, they open up and essentially open up the floodgates as a result of that. Okay, so once it reaches that threshold, all these extra sodium channels open up as a result of the voltage being high enough. Awesome thing. So around the negative 60 mark is where the voltage gated sodium channels open, and you get a massive influx of sodium. Huge influx, all the way up to the positive 30. Okay? At the same time this is happening, we also have those little bits of calcium moving in, but calcium's quite slow at this stage, and it's just the starting point, especially when we're dealing with the heart, because the contraction obviously correlates with the sarcoplasmic reticulum releasing that extra calcium into the body. Okay, so you get a little bit of calcium movement. You get to that positive 30, and then it stops. Now there is the potential, there is enough sodium around these cells to essentially blow up the cell. Okay, there is so much sodium around it, and these voltage gates open at negative 60, but then they have to close. Now obviously if you're a voltage gate channel, you can't just close. Okay, you can't just magically close, because once you're over that voltage, you're going to stay open. So there's a really cool biological function within sodium, voltage gated sodium channels only, and that is a trap door, which is activated when the channels are open, and it has a huge affinity to the other side. Okay, the average of these doors closing is around 0.7 milliseconds after opening. So all this occurs, this massive influx that changes the whole millivolts within the cell occurs in an average of 0.7 milliseconds. Okay, so massive. This influx of sodium obviously increases the millivolts, and in the cases of the heart, correlates to a cardiac contraction. When we move along to phase 1, there's no more sodium movement inside the cell. It just stops. Okay, so sodium channel stops. As you can see, the millivolts starts to drop. Now the reason that occurs is because potassium starts moving out. Okay, calcium starts moving out of the cell. Okay, because now we're at the threshold in which the potassium channels begin to open. Voltage gated potassium channels, it's around your 20, positive 20, positive 25. So because of that, we start to get this decrease. Okay, this is also the time that, because there's a huge influx of sodium on the inside, we're going to get that natural diffusion of sodium out through the general channels as well. Okay, so we start to get this reduction. So this is called the early repolarization phase. Okay, and realistically, you can argue that it's pretty similar to phase 2. Okay, a lot of the same things occur. We need to remember that potassium at this stage is starting to move out because those voltage gates are open. When we look at the phase 2, we have calcium and potassium leaving. Now the reason that is a very, very useful effect is calcium's slow. Okay, calcium is a very slow moving ion. And the reason that is good is because we have this prolonged contraction. And then it sort of holds, and then you start to relax in phase 3. So if it wasn't for the calcium slow movement, and you just relied on that rapid potassium movement, then essentially it would be phase 0, phase 1, 2 would be tiny, and then phase 3 would drop straight down. Okay, and it would not work as well as the contractility of the heart does. Okay, so calcium plays a huge role in that. So you think of calcium as a stabilizing of contraction. Phase 2 is that slow, controlled phase. When we move to phase 3, the calcium gates close. Calcium has moved out, and it starts that reuptake within the sarcoplasmic reticulum. Okay, it starts to move back in. Okay, then a huge amount of potassium flows out. Floodgates are still open for potassium, so it moves out until potassium gets below its threshold. Okay, so as you can see, it actually drops below the threshold, and then you want to use active transport, and that's space neutrality that we talked about, okay, in order to maintain or regulate that equilibrium. Okay, so you may have heard of a sodium potassium pump. Okay, now when we say sodium potassium pump, we're talking about active transport. Now the cool thing about active transport, it essentially will give us positive 10 of our millivolts within our cell. So that's its contribution. Okay, so as you can imagine, it's not a huge contribution. Okay, and what happens is they pump 2 potassium back into the cell and 3 sodium out of the cell every time. And there's hundreds and hundreds of thousands of these happening each time, to the extent that 1/3 of all APD production is utilized with the sodium-potassium pump. Okay, so 1/3 of your energy is spent up just with this sodium-potassium pump transfer. And then, as you can see, once it gets back to its resting phase again, we go back to that phase 4, ready for it again. So it seems like a long process, but this happens very, very quickly. Every time your heart beats, every time you send an impulse, this happens. Millions upon trillions and trillions of times within your body, every millisecond. This is occurring all the time. Now, for those that are following very keenly, you will realize that there is still a shit tin of sodium inside the cell and potassium outside the cell at this stage. Okay, because what's happened is sodium's moved in, calcium sort of movement there for the plateau, and potassium's moved out, and then right at the bottom, when we start to get that equalization back to that normal resting potential, it's just a little bit of potassium and sodium transfer, not all of it. Okay, a lot of people think that all of it is being transferred out, but it's not the case. Now, when you think of big sense, that's okay. Okay, you have to look at the big picture here. So imagine a room that you're sitting in, and right along the outside of the walls is essentially where sodium and potassium is being transferred. But the center of the room, nothing's happening. So it's only at the membrane this occurs. Okay, so we don't need to swap all of them back out, because in the big picture, it really doesn't change the cells that much. Okay, and the millivolts that we're talking about is the millivolts at the membrane inside the cell. That's it. Okay, bringing it into picture. So the pink is what we just looked at. Okay, and that is how it correlates with the QRS. So that's it. Okay, so when the contraction comes in, massive sodium between Q and R, and then as the potassium and the calcium start to move, obviously that's the finishing of the contraction. And it's not until phase 3 that we actually get that depolarization of the ventricle with the T wave. And to take it one step further, just to finish off, I promise, we can start looking at that relationship that we have with drugs. Okay? So when we're dealing with classes of drugs, see there's 3 class 1s, sodium channel blockers, and essentially it breaks up to how well or how fast acting they are in blocking those channels. Because remember, there's many different sodium channels. Some will block the permeable ones, some will block the voltage-gated ones. Okay, but they're all classed as class 1 channel blockers. Calcium channel blockers are class 4. Okay, and as we know now, that calcium has that prolonged, that prolonging plateau phase plays a big role there. So a calcium channel blocker is obviously going to play a big role in that phase 2. Okay, class 3 channel blocker is going to play a big role in that repolarization phase that we talked about. So when we look at amiodarone, it's mostly a potassium channel blocker. So when they say it prolongs that refractory period, it essentially means it's going to take longer for those potassium to move out of the cell. Okay, a lot longer for potassium to move out of the cell, which means it's going to slow down your heart rate. Okay, because it's taking longer to get back to that resting potential. Okay, and hopefully a little bit of automaticity might kick in. Okay, and the class 2 is your beta blockers. Okay, so that's slowing down that impulse of beta coming in. That's how it all relates. That's why understanding this concept can be handy. And when in future lessons we start looking at the actual ECG and what we're reading, we can start to get a better understanding of what's actually happening in the body when the heart contracts. I understand that there was a lot of concepts to cover. Okay, realistically this should be a broken up 4-hour lesson. If you have any questions,
Please feel free to ask in the comment section. And until next time, take care.